Namaste, tutor. I'm really keen to dive deep into a fundamental topic today. It's crucial for our Class 10th board exams, and honestly, for competitive exams like UPSC, SSC, and others too. I'm talking about acids, bases, and salts. It sounds simple maybe on the surface, but I know there's quite a lot of depth we need to cover to really succeed in exams.
Welcome to this deep dive and namaste. You've absolutely picked a key area. Acids, bases, and salts really are the bedrock for so much in chemistry, aren't they? Today we'll go far beyond just the basic definitions. Our mission, if you will, is to explore their unique chemical properties, what they all fundamentally have in common, how we can precisely measure their strength, and critically, their incredible practical applications. In our daily lives and right across various industries. This session is really tailored to make sure you grasp every nuance needed, not just for theory, but for mastering problem solving in your exams. We're going to break down these complex ideas step by step, make sure they really stick.
Okay, great. Let's unpack this then. Maybe starting with the very basics, stuff we probably learned in junior classes, but perhaps with a bit more scientific rigor now.
Absolutely. Good place to start. Before we get into the detailed reactions and industrial stuff, let's nail down the basics. What are acids and bases, fundamentally? So, in simple terms, acids are like the proton donors in chemistry. They're substances that release hydrogen ions, often written as H+ when they're in a solution. And it's these H+ ions that give acids their typical characteristics, like that sharp, sour taste you get from lemon juice or, say, vinegar. On the flip side, you have bases. They're the counterparts, the proton acceptors. They tend to release hydroxide ions, that's OH, in solution. And these OH ions are what usually make bases feel a bit soapy or slippery to touch. And they often have a bitter taste, like baking soda dissolved in water. Now, while taste and feel give you a quick idea, it's really important to remember, and I can't stress this enough in any scientific setting, tasting or touching chemicals is a big no-no. Safety first. Many can be corrosive or harmful.
Oh, okay. So the old primary school idea of tasting is just a starting point, definitely not the scientific way to test them. So how do we scientifically identify them without, tasting or touching, given the safety risks?
Precisely. Safety is absolutely paramount. And that's exactly where indicators come into the picture. These are really quite remarkable substances. They show a distinct, visible color change when they come into contact with either an acidic or a basic medium. Think of them as, like, chemical traffic lights, signaling the nature of the solution. Let's start with some you might even find around the house, the natural indicators. One of the most common and probably oldest natural indicators used widely in labs is litmus. Litmus isn't just one thing. It's actually a purple dye extracted from lichen. Lichen itself is fascinating, a symbiotic partnership between a fungus and an alga belonging to the thallophyta division. When litmus solution is neutral, so either acidic nor basic, its natural color is purple. But it shows very clear and predictable color changes when you put it in acids or bases. And these changes are vital for your practical exams. Acids will always change blue litmus paper to red. Remember, acid red. While bases do the opposite. They change red litmus paper to blue, base mellow blue. This simple tool is really a cornerstone for basic acid-base identification.
Okay, litmus blue to red for acid, red to blue for base. Got it. What about other natural ones? You mentioned household items.
Yes, another fantastic one, literally found in almost every Indian kitchen, is turmeric haldi. You've probably seen its indicating properties yourself, maybe without even thinking about it chemically. Imagine spilling some curry, which has turmeric, of course, on a white shirt, a classic mishap. When you go to wash it and scrub soap, which is typically basic, onto that yellow stain, what happens?
It turns reddish-brown. I've definitely seen that happen.
Yeah, exactly. That reddish-brown color appears because the turmeric is reacting to the basic nature of the soap. Then, when you rinse the cloth thoroughly with lots of water, washing away the soap, the stain usually turns yellow again. This color change really clearly shows turmeric's ability to act as a natural acid-base indicator. It's yellow and acid-neutral, reddish-brown, and base. And beyond litmus and turmeric, nature provides others too, things like the leaves of red cabbage or even the colored petals of flowers like hydrangea, petunia, and geranium. They also show distinct color changes with acids and bases. So these are all broadly called natural acid-base indicators, nature's own chemistry toolkit, you could say.
That's really clear. So we have these natural options, which are quite resourceful, but for, say, precise lab work, what are these synthetic indicators the source mentioned? Are they, more reliable?
Excellent question. Yes, for more precise, consistent, and reliable testing, especially in a controlled lab environment, we often turn to synthetic indicators. These are specific chemical compounds synthesized purely for this purpose. They offer very sharp and consistent color changes. The two most common ones you absolutely need to know for your board exams and any competitive quizzes, really, are phenolphthalein and methyl orange. Phenolphthalein is quite distinctive. In an acidic solution, it remains completely colorless. Looks just like water. But the moment you add it to a basic solution, bang, it turns a vibrant, unmistakable pink.
Okay. Colorless in acid, pink in base. That's phenolphthalein.
Correct. Now, methyl orange behaves differently. It turns a striking red color in an acidic solution. In a basic solution, it turns yellow. So red in acid, yellow in base. These precise color changes, colorless pink for phenolphthalein, red-yellow for methyl orange, are frequently tested. MCQs, Practical Viva, you name it. So definitely commit these to memory. They're essential for things like titrations.
This is very clear, tutor. Natural, synthetic. Got it. But then the source mentions olfactory indicators. That sounds interesting. Does their smell change? How would that even work?
That's a sharp observation. And yes, it points to a very clever and inclusive application in chemistry. You've grasped the core idea perfectly. Olfactory indicators are substances whose odor changes, or in some cases disappears completely, depending on whether they're placed in an acidic or a basic medium. This method is particularly useful, for example, for visually impaired students who can't perceive color changes, or simply as another method of identification. Let's walk through an activity like Activity 2.2 from your source to see how this works with common things like onion, vanilla essence, and clove oil. Okay, imagine preparing this. You take some finely chopped onions, put them in a clean plastic bag with a few strips of clean cloth. Tie the bag tightly, leave it overnight in the fridge. By morning, those cloth strips will have absorbed that characteristic strong onion smell. First step is always to check that natural odor.
Okay, so the cloth smells like onions. Then what?
All right, now take 2 of these onion-scented strips. On one, you carefully add a few drops of dilute hydrochloric acid, HCl, a common acid. On the other strip, you add a few drops of dilute sodium hydroxide solution, NaOH, a strong base. Let them sit for a moment to react, then gently rinse both strips with a little water and check their odor again. What you'd notice quite distinctly is this. The strip treated with the acid. It still smells strongly of onions, the odor remains. But the strip treated with the base, the smell is gone, or at least significantly reduced. The pungent onion odor basically vanishes in the basic medium.
Wow, okay, so the smell disappears with the base. Does it work the same for vanilla and clove oil?
Pretty much the same principle, yes. You'd start by noting their distinct natural smells. Vanilla's sweet scent, clove's spicy one. Then, in separate test tubes for each, you'd add a few drops of dilute HCl to one sample and dilute NaOH to another, along with the vanilla or clove oil. Shake them well, let them sit, and you check the odors again. The observation is consistent. Vanilla essence and clove oil. They keep their characteristic smell in the acidic medium. But in the basic medium, they lose their smell. It disappears. So based on these observations, we could definitely say that onion, vanilla, and clove oil act as olfactory indicators. The change, or loss of smell, gives a clear signal about the medium, another tool in our identification kit.
That's fascinating. So if someone couldn't see the color change, they could still test for acid or base using smell. Really clever.
Precisely. It's about having different methods available. Now, we've covered identification quite well, I think. Let's move on to the core of their chemical behavior. This is really where most exam questions come from. How acids and bases actually react with other substances. This is where we see their chemical power in action.
Okay, reactions. Let's take this step by step. Maybe start with how acids react with metals. What happens there?
Good starting point. The reaction of acids with metals is a very common, significant one, and it's a classic experiment for your practicals too. Let's visualize Activity 2.3, reacting zinc granules with sulfuric acid. Imagine a test tube. You put a few small, shiny zinc granules in the bottom. Then carefully you pour in about 5 milliliters of dilute sulfuric acid, H2SO4, just enough to cover them. What happens almost right away?
Bubbles. Fizzing.
Exactly. You'd see a flurry of bubbles rising from the surface of the zinc. Vigorous fizzing. That's a clear sign a gas is being produced. Now, how do we know what gas it is? We need to test it. You'd connect a delivery tube and pass this gas through some soap solution. As the gas bubbles through, it forms soap bubbles filled with this unknown gas. These bubbles float up, and here's the key test. You bring a burning candle, or maybe a lit matchstick, near one of these gas-filled bubbles. What happens? A distinct pop sound, like a tiny explosion.
The pop sound, I remember that. That's for hydrogen gas, right?
Absolutely correct. That pop sound is the characteristic definitive test for hydrogen gas, H2. You must remember that test. And you can repeat this with other common acids, HCl, HNO3, even acetic acid, CH3COH. Generally, you'll see the same result. hydrogen gas evolution. So we can summarize the general reaction pattern. Acid plus metal, salt plus hydrogen gas. A very common example equation you should know and be able to balance is 2HCl plus ZnS, ZnCl2aq plus H2G. Zinc chloride salt plus hydrogen gas. What's happening chemically is the metal, if it's reactive enough, displaces the hydrogen from the acid. It kicks the hydrogen out, forming hydrogen gas and leaving behind a salt. This comes up a lot in exams.
Okay, so acids react with metals to give hydrogen gas and a salt. Clear pattern. What about bases? Do they react with metals in the same way, or is there a catch?
That's a very perceptive question. Yeah. And yes, there is a crucial difference, a catch, you need to be aware of. Let's look at activity 2.4, reacting sodium hydroxide, a strong base, with zinc. If you take some sodium hydroxide solution, NaOH, with zinc granules in a test tube, and perhaps warm it gently, you will observe the formation of hydrogen gas again. You can confirm it with the same pop sound test. The reaction here is 2NaOH plus the NOS, A Na2ZnO2s plus H2G. That Na2ZnAO2 is a salt called sodium zincate.
So bases can react with metals to give hydrogen too.
But, and this is the really important caveat, especially for competitive exams, this reaction, base plus metal E salt plus H2, is not possible with all metals. Unlike acids, which generally react with most metals above hydrogen in the reactivity series, this reaction with bases is much more selective. It really only happens with certain metals like zinc and aluminum when they react with strong alkalis like NOH. So while both can produce hydrogen gas with some metals, the reaction with bases is far less general. That selectivity is a key distinction often tested.
Got it. Acids are generalists with metals, bases are specialists. That's a really important difference. Okay, what about carbonates and hydrogen carbonates? Things like washing soda, baking soda, limestone, they're everywhere. How do acids react with them?
Excellent question. Reactions with metal carbonates and metal hydrogen carbonates are absolutely crucial. They explain effervescence, the lime water test, things you'll definitely encounter. Pay close attention here. Let's imagine activity 2.5. Two test tubes, A and B. In A, you put about half a gram of sodium carbonate, Na2CO3, that's washing soda. In B, about half a gram of sodium hydrogen carbonate, NaHECO3, that's washing soda. Then to both test tubes, you carefully add about 2 milliliters of dilute hydrochloric acid, HLAL. What's the immediate observation in both?
More fizzing, like with the metals.
Exactly, but this time it's usually even more vigorous. We call it effervescence. Rapid bubbling, fizzing, indicating a gas is being produced very quickly. Now, the crucial test. How do we identify this gas? We use the lime water test. You pass the gas evolved from each test tube through a delivery tube into another test tube containing lime water. Lime water is just a clear solution of calcium hydroxide, KOH2. What happens to the clear lime water when this gas bubbles through?
It turns milky white.
Precisely. That milky white appearance is the classic definitive test for carbon dioxide, CO2 gas. Why does it turn milky? Because the CO2 reacts with the calcium hydroxide to form an insoluble white precipitated calcium carbonate, KCO3. The reaction is KKOG plus CO2G plus HCO3. That solid KCO3 makes the solution look milky or cloudy.
Okay, so CO2 turns lime water milky, is that it?
But there's a little more to it, a detail often used in trickier questions, especially in competitive exams. What happens if you keep bubbling excess carbon dioxide through that milky lime water?
Does it stay milky?
Actually, no. If you pass excess CO2, the milky white precipitate disappears, and the solution becomes clear again.
Really? Why?
It's because the calcium carbonate, CCO3, reacts further with the excess CO2 in the water present to form something called calcium hydrogen carbonate, KHCO32. The reaction is KCO3s plus H2O plus CO2G at KHCO32A, and the key thing is calcium hydrogen carbonate is soluble in water, so the precipitate dissolves and the solution clears up. That disappearance on adding excess CO2 is also characteristic.
Wow, okay. That's a subtle but important detail. So what's the overall reaction when acids react with carbonates or hydrogen carbonates?
The general pattern is metal carbonate, metal hydrogen carbonate plus acid E salt plus carbon dioxide plus water. So for sodium carbonate reacting with HCl, it's Na2CO3 plus 2HClQ, 2NaClQ plus H2O plus CO2G. You get sodium chloride, salt, water, and CO2. And for sodium hydrogen carbonate with HCl, it's similar. HCO3s plus HCl plus H2L plus CO2G. Same product, just different balancing. And this reaction has real-world relevance too. Limestone, chalk, marble, they're all just different forms of calcium carbonate. AgCO3. This reaction also explains why you shouldn't keep sour things like curd, which contains lactic acid, or pickles in brass or copper vessels. The acid can react with the metal itself, or often with a layer of metal carbonate that might form on the surface over time. This reaction can produce potentially harmful compounds, making the food unsafe. It's a common practical application question.
Right, the lime water test for CO2 is key. And the excess CO2 detail is great for competitive exams. Very helpful. Now, we've seen acids react with metals, carbonates. What happens when acids and bases, these chemical opposites, react directly with each other? I think you mentioned neutralization earlier.
Indeed, neutralization is a cornerstone reaction in acid-base chemistry. It's essentially how acids and bases chemically cancel out or nullify each other's characteristic properties. They react to form something much milder, usually neutral. Let's explore activity 2.6 to see this visually. Imagine you take about 2 milliliters of dilute sodium hydroxide solution, NaOH, a strong base, in a test tube. Then you add just a couple of drops of phenolphthalein indicator.
Okay, NOH is basic, so phenolphthalein will turn it pink.
Exactly. The solution immediately turns a distinct pink color. Now the next step is crucial. You slowly, carefully add dilute hydrochloric acid HCl solution, a strong acid, drop by drop into the pink solution, swirling gently after each drop. What do you think you'll observe as you keep adding the acid?
The pink color will fade and eventually disappear.
Precisely. The pink color gradually disappears and the solution becomes colorless again. This happens because the acid, HCl, is neutralizing the base, NaOH. When just enough acid has been added to completely react with all the base, the solution becomes neutral. And in a neutral solution, phenolphthalein is colorless.
Okay, so the disappearance of pink shows neutralization is complete.
Right, and to really drive the point home, you can take it one step further. What if you now add just 1 or 2 more drops of the NaOH solution back into the now colorless mixture?
The pink color would come back because it's basic again.
Perfect. The pink reappears because you've added excess base, making the solution alkaline again, and phenolphthalein turns pink in alkaline conditions. This back and forth beautifully shows the neutralization point and how indicators work. So the general reaction summary for neutralization is simple and vital. Base plus acid salt plus water, the classic example. Agar-HE plus HCl-AQ plus H2O-AQ. Sodium hydroxide plus hydrochloric acid gives sodium chloride, common salt, and water. But for a deeper understanding, especially for higher exams, the ionic view is key. What's really reacting, it's the hydrogen ions H plus from the acid and hydroxide ions from the base. They combine. The core ionic reaction of neutralization is simply H plus AQ plus OH AQ. What's the heart of it? An H plus ion meets an OH ion and forms a water molecule.
That ionic equation really simplifies it down to the essential chemistry. H plus plus OH makes water. Very insightful. Now, what about oxides? We have metal oxides, non-metal oxides. Do they fit into this acid-base picture?
Excellent question. Oxides are everywhere, and yes, they play a significant role. We can classify them based on their acidic or basic behavior by seeing how they react. Let's start with metallic oxides. Think about activity 2.7, reacting copper oxide with hydrochloric acid. You take a small amount of copper oxide, CuO, to the black solid powder, put it in a beaker, then slowly add dilute hydrochloric acid, HCl, while stirring. What you'll see is quite noticeable. The black solid, the CuO, gradually dissolves, and at the same time, the solution turns a distinct blue-green color.
Blue-green, what causes that color?
That specific blue-green color is the signature of copper to chloride, CCl2, being formed in the solution. So the general reaction type here is metal oxide plus acid plus water. In this specific case, copper oxide plus 2HCl2, He plus H2O. Copper oxide plus hydrochloric acid gives copper chloride, salt, and water. Now think about that reaction pattern. Something reacts with an acid to give salt and water. What does that remind you of?
That's just like the neutralization reaction, base plus acid, salt plus water.
Exactly. Since metallic oxides react with acids in the same way the bases do, producing salt and water, we conclude that metallic oxides are generally basic oxides. They exhibit basic properties.
Okay, so metal oxides are basic. What about non-metal oxides, like CO2?
Good connection back. Let's consider non-metallic oxides. Remember activity 2.5, where carbon dioxide, CO2, a non-metallic oxide, reacted with lime water. Lime water is calcium hydroxide, KOH2, which is a base. And what did we form?
Calcium carbonate, TTO3, which is a salt, and water, H2O.
Right, the reaction was KKOH to AQ plus CO2G3 plus H2OL. Look at the pattern again. Base KOH2 plus non-metallic oxide, CO2, salt KCO3 plus water. This reaction looks very much like a base plus acid salt plus water neutralization reaction, doesn't it?
It does. So does that mean non-metallic oxides are acidic?
Precisely. We conclude that non-metallic oxides are generally acidic in nature. They behave chemically like acids. This concept also helps explain things in the real world, like acid rain. Even clean rainwater is slightly acidic because CO2 from the atmosphere dissolves in it, forming carbonic acid, H2CO3. That's a nonmetallic oxide showing its acidic nature. This is a vital concept.
We've seen all these different reactions, acids with metals, carbonates, bases, oxides acting basic or acidic. But what's the single underlying thing? What makes an acid and a base at the most fundamental level? This seems really important for deeper understanding.
You're absolutely right. Getting to that common factor, the essence of acidity and basicity, is key. Let's start with acids. What did we observe in activity 2.3? All the acids we tested, HCl, H2SO4, HNO3, even CH3COH, produced what gas when reacting with metals?
Hydrogen gas, H2.
Right. That strongly suggests hydrogen is common and crucial to all acids. But does just having hydrogen make something an acid? Think about glucose, C6H12O6, or alcohol, like ethanol, C2H5OH. They both contain hydrogen atoms. Are they acidic?
I don't think so. They don't taste sour like acids.
Exactly. So just having hydrogen isn't enough. We need a way to test their behavior in solution. That brings us to the conductivity test, activity 2.8. Imagine setting up a simple circuit. A beaker with two nails acting as electrodes, connected to a 6-volt battery, a small bulb, and a switch. The solution in the beaker completes the circuit. First, pour dilute HCl into the beaker, immerse the nails, flick the switch. What happens?
Bulb glows.
Correct. Repeat with dilute H2SO4.
Bulb glows again, brightly.
Okay. Now rinse everything and repeat the exact same test, but this time using a glucose solution.
Does the bulb glow? I suspect.
You suspect correctly. The bulb does not glow. Same result if you use an alcohol solution. The bulb stays dark.
So acids conduct electricity, but glucose and alcohol don't, even though they all have hydrogen. Why?
What allows electricity to flow through a solution?
Moving charges. Ions.
Precisely. Mobile ions. The glowing bulb tells us that the acid solutions contain freely moving ions that can carry the electric current. Acids like HCl, H2SO4, HNO3, CH3COH all dissociate or ionize in water to produce hydrogen ions, H+, as their common positive ion. HCl gives H+ and Cl, H2SO4 gives H+ and SO42. These mobile H+ ions and the negative ions carry the current. Glucose and alcohol, although they contain hydrogen atoms in their molecules, do not ionize in water. They don't produce free ions. So the crucial conclusion, acids produce hydrogen ions, H+, He in solution, and it's these H+ ions that are responsible for their acidic properties, including conductivity.
Okay, H+ ions are the key for acids. What about bases then? What's the common factor there? Is it similar?
Very similar logic. If you were to continue activity 2.8 and test solutions of bases, like sodium hydroxide, NaOH, or calcium hydroxide, CaOH2, you'd find that the bulb glows brightly for them too. This indicates that bases also produce mobile ions in solution. And the common ion generated by bases when they dissolve in water is the hydroxide ion, OH. So just as H+ ions are responsible for acidic properties, it's the hydroxide ions, OH, generated in solution that are responsible for basic properties. And this leads to an important definition, alkali. Bases that are soluble in water are specifically called alkalis. Examples are NaOH, KOH. They feel soapy, taste bitter, or corrosive. But remember, not all bases dissolve well in water. For example, copper hydroxide is a base, but it's practically insoluble. So it's not an alkali. All alkalis are bases, but not all bases are alkalis. That distinction sometimes comes up.
So it boils down to H+ ions for acids and OH ions for bases in water, making them conduct electricity and giving them their properties. Simple enough. But wait, the source mentioned something about H+ ions not existing alone, that they form H3O+ line. Can you elaborate on that? Sounds like a finer point, maybe important for accuracy.
Excellent point. And yes, you're right. It is crucial for precise chemical understanding, especially as you move to higher levels. While we often write H+ for simplicity, it's not the full picture in water. Think about it. An H+ ion is just a proton, a tiny, positively charged particle. It's highly unstable and extremely reactive on its own in an aqueous environment. It simply can't hang around by itself. So what happens? It immediately latches onto a water molecule. Let's illustrate this with activity 2.9. Imagine you generate dry hydrogen chloride gas, HCl. You could do this by reacting solid sodium chloride, NaCl, with concentrated sulfuric acid, H2SO4. Make sure everything is dry. Now test this dry HCl gas first with a piece of dry blue litmus paper. Then immediately test it with a piece of wet, dampened with water, blue litmus paper.
Okay, dry HCl gas with dry litmus. I guess nothing happens.
Correct. The dry HCl gas does not change the color of the dry litmus paper. It's not acting like an acid yet.
But with the wet litmus paper.
Now the wet blue litmus paper instantly turns red.
So it needed the water.
Exactly. This experiment clearly shows that the acidic properties of HCl, producing H+ ions, are only exhibited in the presence of water. The separation of H plus from the HCl molecule, the ionization, requires water as the medium. So what really happens to that H plus ion once it's formed in water? It's strongly attracted to the polar water molecules, H2O. It combines with the water molecule to form a hydronium ion, H3O plus He. The reaction is HCl plus H2O plus HU plus Cl Ig, or more generally for the proton itself, H plus HCO plus H3. So strictly speaking, when we talk about acidity in water, we're talking about the concentration of hydronium ions, H3O plus Neo. Although often, for simplicity, especially at the class 10 level, we still just write H plus AQ. But you should know H2O plus is the more accurate representation of water.
H3O plus Aristo, the hydronium ion. Got it. That makes sense. And bases just release OH directly into the water.
Yes, soluble bases, alkalis, dissociate in water to directly release hydroxide ions. For example, solid NaOH dissolves and ionizes. NaOHS, water Na plus AQ plus OHU. Similarly, KOHS, water K plus AQ plus OHAQ. Even sparingly soluble ones like MgOH2S release some ions, MgOH2 and Mg2 plus 2OHAQ. And this brings us back to neutralization, viewed ionically again. It's the H plus, or more accurately HCO plus, from the acid reacting with the OH from the base, H plus AQ plus OH2U, that fundamental reaction.
Okay, the role of water is crystal clear now. It's not just a passive solvent. It's actively involved in forming the ions. Now, speaking of water, the source also mentions diluting acids and bases. Are there specific safety precautions? It sounds like something you need to be careful with.
You are absolutely right to focus on safety here. This is critically important in the lab, and honestly, it's a very common question, often carrying significant marks in both practical exams and theory papers. The process of dissolving a concentrated acid or concentrated base in water, which we call dilution, is a highly exothermic process. What does exothermic mean?
It releases heat, gets hot.
Exactly. It releases a significant amount of heat energy. Let's visualize activity 2.0. Take about 10 milliliters of water in a sturdy glass beaker. Then, very slowly and carefully, add just a few drops of concentrated sulfuric acid, H2SO4, down the side of the beaker while continuously swirling gently. Now, carefully touch the base of the beaker. What would you feel?
It would feel warm or even hot.
Definitely. It becomes noticeably warm, sometimes quite hot, depending on the concentration and amount. You'd observe the same thing if you dissolve solid sodium hydroxide pellets in water. This warmth is direct evidence of the exothermic nature of dissolution. Now, for the absolute vital safety rule, the one mantra you must never forget: always add acid or concentrated base slowly to water with constant stirring. Never add water to the concentrated acid. Repeat that in your head. Acid to water, A to W.
Okay, acid to water, got it. But why is it so important? What happens if you do it the wrong way around?
The reasoning is crucial. If you add water to a concentrated acid, like H2SO4, the first few drops of water encounter a large amount of acid. The heat released is immense and highly localized in that small amount of water. This localized extreme heat can instantly turn the water into steam. This causes the mixture to splash violently out of the container. We call this spitting. And that splash contains concentrated corrosive acid. It can cause severe chemical burns to skin, eyes, clothes. Additionally, the rapid, uneven heating of the glass container can cause thermal stress, potentially cracking or even shattering the beaker. It's genuinely dangerous. That's why you always add the acid slowly to the larger volume of water, allowing the heat to dissipate more safely throughout the water volume, especially with stirring.
Wow, okay, that makes perfect sense. Acid to water, slowly with stirring. Never forget. So what's the actual effect of dilution chemically?
Chemically, when you mix an acid or base with water, you're increasing the total volume of the solution without increasing the amount of acid or base molecules. This means the concentration of the active ions H3O plus for acids, or OH for bases per unit volume, decreases. The solution becomes less concentrated, less potent. We call this process dilution, and the resulting solution is said to be diluted. It effectively reduces the strength or corrosive power of the acid or base.
Right, so dilution makes it weaker in terms of concentration. This makes me wonder, how do we actually quantify that strength? Is there like a scale for how acidic or basic something is beyond just strong or weak?
You're anticipating the next crucial concept perfectly. Yes, indeed. Simply saying strong or weak isn't always precise enough. We need a quantitative way to measure the acidity or basicity, specifically by measuring the hydrogen ion concentration. And for that, we have a very elegant tool, the pH scale. Before the pH scale was developed, we relied on individual indicators like litmus or phenolphthalein. They're great for telling you if something is acidic or basic, but they don't tell you how acidic or how basic it is. Is it just Slightly acidic or extremely acidic. Litmus can't tell you that.
Right, they're more like on-off switches.
Exactly. So scientists developed something called the universal indicator. This isn't a single chemical, but a carefully prepared mixture of several different indicators. When you add universal indicator solution, or use universal indicator paper, to a substance, it doesn't just turn one color. It shows a whole spectrum of different colors, depending on the exact concentration of hydrogen ions in the solution. Each color corresponds to a different level of acidity or basicity. Much more informative.
Okay, so the universal indicator gives a range of colors.
Building on that idea, a Danish chemist named Sørensen developed a numerical scale specifically for measuring hydrogen ion concentration, the pH scale. The P in pH comes from the German word Potenz, meaning power. So you can literally think of pH as representing the power of hydrogen ions in a solution. The scale typically runs from 0 to 14, though it can technically go beyond these limits in extreme cases. 0 to 14 covers almost everything we encounter.
0 to 14, how do we interpret the numbers?
This is critical. It works on an inverse relationship with hydrogen ion concentration. The higher the concentration of hydronium ions, H3O+, or H+, the lower the pH value. More H+ means more acidic, which means a smaller number on the pH scale. A perfectly neutral solution has a pH of exactly 7. Pure distilled water is the classic example. Acidic solutions always have pH values less than 7. As the pH value decreases from 7 down towards 0, the acidity increases. So pH 1 is much more acidic than pH 6. Basic or alkaline solutions have pH values greater than 7. As the pH value increases from 7 up towards 14, the alkalinity increases. This also means the concentration of OH ions increases. So pH 13 is much more basic than pH 8.
Lower pH means more acidic, higher pH means more basic, 7 is neutral. Got it. How is it usually measured in a lab?
In most school labs, the common method is using pH paper. This is paper that's been impregnated with the universal indicator. You dip a small strip into the solution you want to test. The paper changes color. You can immediately compare that color to a standard color chart that comes with the pH paper. Each color on the chart corresponds to a specific pH value, usually in whole number steps, like pH 1, 2, 3, and so on. It gives you a quick approximate measure of the pH. More precise measurements use electronic pH meters.
Okay, pH paper gives a quick estimate, and this scale directly relates to the idea of strong versus weak acids and bases.
Absolutely. The pH scale provides the quantitative basis for understanding strength. The strength of an acid or base depends directly on the concentration of ions it produces in solution. Strong acids, like HCl or H2SO4, ionize almost completely in water. They release a lot of H+ ions. So a solution of a strong acid will have a very low pH, typically 0.3 depending on concentration. Weak acids like acetic acid, CH3COH, and vinegar only ionize partially. They release fewer H+ ions compared to a strong acid of the same concentration. So their pH will be higher, closer to 7, maybe pH 3.6, but still less than 7. Similarly, strong bases like NaOH or KOH dissociate completely to give a high concentration of OH ions. This results in a very high pH, typically 12, 14. Weak bases like ammonium hydroxide, NH4OH, or magnesium hydroxide, MgOH2, produce fewer OH ions. Their pH will be basic above 7, but lower than strong bases, maybe pH 8, 11.
So strength is about how many ions they release, which directly impacts the pH value.
Precisely. And this difference in ion production explains reaction rates, too. Remember we said HCl reacts faster with metals than acetic acid. That's because, at the same concentration, the strong acid HCl produces far more H+ ions, leading to more frequent collisions and a faster reaction, hence more vigorous fizzing. The pH tells you about that ion concentration.
That connects everything nicely. pH isn't just about acid-base, but also concentration of ions and therefore strength and reactivity.
Wow. So how does this pH value actually impact our daily lives and the environment? It feels like it must be incredibly important if our bodies work in such a narrow range. You've hit on a crucial point. The importance of pH extends far beyond the chemistry lab. It's fundamental to life in the environment, which is why it's such a frequent topic in exams, from boards to UPSC. Let's start with the pH sensitivity of living organisms. As you mentioned, our own bodies, and most life forms, operate within a very tight pH window, typically between 7.0 and 7.8, slightly alkaline. Significant deviations from this range can disrupt vital biological processes like enzyme function and can be harmful or even fatal. Survival depends on maintaining this delicate pH balance. This sensitivity is dramatically highlighted by the problem of acid rain. When the pH of rainwater drops below 5.6 due to pollutants like sulfur dioxide and nitrogen oxides dissolving, we call it acid rain. When this acidic water flows into rivers and lakes, it lowers the water's pH. This can devastate aquatic ecosystems, making it incredibly difficult for fish, insects, and aquatic plants to survive. It's a major environmental issue.
So acid rain directly impacts aquatic life because they can't handle the pH change. What about on land? Soil pH.
Absolutely critical for agriculture. Soil pH affects plant growth significantly. Different plants have specific pH ranges they prefer for optimal growth and nutrient uptake. Farmers regularly test their soil pH. If the soil is too acidic, low pH, plants might struggle to absorb nutrients. To counteract this, farmers often add substances like quicklime, CaO, slaked lime, COH2, or chalk, KCO3. These are all basic compounds that help neutralize the excess acidity. Conversely, if the soil is too alkaline, high pH, they might add organic matter. As organic matter decomposes, it releases acids, which can help lower the soil pH back towards a more suitable range. So managing soil pH is key to good crop yields.
Okay, soil pH for plants. What about inside us? Our digestive system? You mentioned our stomach is acidic.
Yes, the pH in our digestive system is a fascinating example of biological control. Our stomach produces hydrochloric acid, HCl, with a very low pH, maybe around 1.5 to 3.5. This highly acidic environment is essential for digestion. It helps break down food and also kills most harmful bacteria we might ingest. Our stomach lining is specially adapted to withstand this acidity, but sometimes, especially during indigestion, the stomach produces too much acid. This causes that familiar burning sensation, pain, and irritation, heartburn.
Right, and that's when people take antacids.
Exactly. People use antacids, which are essentially mild bases. A very common one is magnesium hydroxide, MgOH2, often sold as milk of magnesia. Other bases like calcium carbonate or sodium hydrogencarbonate are also used. These bases neutralize the excess stomach acid, raising the pH back to a more comfortable level and providing relief. It's a direct application of the neutralization reaction we discussed.
Simple chemistry saving the day. What about teeth? Does pH affect them?
Oh, definitely. pH change is the main cause of tooth decay. Our tooth enamel, the hard outer layer, is made of calcium hydroxyapatite, a crystalline form of calcium phosphate. It's the hardest substance in our body. However, despite being hard, enamel starts to corrode or demineralize when the pH in the mouth drops below 5.5.
Below 5.5, what makes the mouth acidic?
Bacteria. There are bacteria naturally present in our mouths. When we eat sugary foods or leave food particles behind, these bacteria feed on the sugars and food debris. As they metabolize these sugars, they produce acids as a waste product. Lactic acid is a common one. If these acids build up, the pH drops. If the pH stays below 5.5 for extended periods, the enamel starts dissolving, leading to cavities.
So how do we prevent that?
The best defense is good oral hygiene. Cleaning your mouth thoroughly after eating removes the food particles the bacteria feed on, and using toothpaste is also key. Most toothpastes are generally basic, alkaline. They help neutralize the acids produced by bacteria and can also contain fluoride, which helps strengthen enamel.
Makes sense. Neutralize the acid, protect the enamel. Any other everyday pH examples?
One more interesting area is self-defense in nature chemical warfare, using pH. Think about a bee sting. It injects an acidic substance, often formic acid, also called methanoic acid, which causes that sharp pain and irritation.
Ouch. So what's the remedy?
Applying a mild base helps. Baking soda, sodium hydrogencarbonate solution, is a common home remedy. The base neutralizes the acid from the sting, providing relief. Similarly, the stinging hairs of the nettle plant inject methanoic acid, causing a burning pain. Interestingly, the dock plant, which is often found growing near nettles, has leaves that are basic. Rubbing a dock leaf on a nettle sting is a traditional remedy that works by neutralization.
Nature's own little pharmacy.
Exactly. And for exams, it's useful to be familiar with Table 2.3 in your source, which lists common natural acids and their sources: acetic acid, vinegar; citric acid, lemons, oranges; lactic acid, curd; tartaric acid, tamarind; oxalic acid, tomatoes; methanoic acid, ant sting, nettle sting. These often appear in MCQs.
That's a great overview of pH in action everywhere. Really drives home its importance. Okay, we've covered acids, bases, pH. Now let's shift focus to salts. They're the products of neutralization. But what else should we know about them? Are they all just like table salt?
Good transition. Salts are indeed much more diverse and fascinating than just NaCl. Let's start by thinking about the family of salts. Just like elements belong to families in the periodic table based on shared properties, we can group salts into families. Salts belong to the same family if they share the same positive ion, so gation of the same negative ion.
Yeah.
For example, sodium chloride, NaCl, and sodium sulfate, Ne2SO4. What do they have in common?
The sodium ion, Na+A.
Right. So they both belong to the family of sodium salts. What about sodium chloride, NaCl, and potassium chloride, KCl?
They both have the chloride ion,
Yeah,
Cl.
correct. So they belong to the family of chloride salts. Understanding these families helps us predict and compare properties. Activity 2.13 in your text gives you practice identifying families from a list, good exercise for exams.
Okay, so families are based on shared ions. Now back to pH. You said NaCl is neutral, but are all salts neutral? Or does their parentage, the acid and base they came from, affect their pH?
That's the crucial question. And the answer is no, not all salts are neutral. This is a very common misconception and an important point for exams. The pH of a salt solution depends entirely on the relative strengths of the acid and base that formed it. Activity 2.14 involves testing various salt solutions like NaCl, KNO3, LCl3, ZnSO4, QSO4, CH3 NaCO3, NaHCO3 with litmus or pH paper to see if they're acidic, basic, or neutral. Here are the key rules you absolutely must remember. 1. Salt strong acid plus strong base. This combination produces a neutral salt solution with a pH of exactly 7. Example, NaCl from strong acid HCl plus strong base NaOH, or KNO3 from strong acid HNO3 plus strong base KOH. Example, ammonium chloride NH4Cl from strong acid HCl plus weak base NH4OH, or copper sulfate KuSO4 from strong acid H2SO4 plus weak base DOH2. 3. Salt of strong base plus weak acid. This results in a basic alkaline salt solution with a pH greater than 7. The strong base parent dominates. Example, sodium acetate CH3CO now from strong base NaOH plus weak acid CH3COOH, or sodium carbonate Na2CO3 from strong base NaOH plus weak acid H2CO3.
What about weak acid and weak base?
Salt of weak acid plus weak base. This one is trickier. The pH depends on the relative strengths of the weak acid and weak base. It could be slightly acidic, slightly basic, or even neutral. But usually you don't need to predict the exact pH for these at the class 10 level. Just be aware they exist.
Okay, those first 3 rules are key. Strong. Strong is neutral. Strong acid weak base is acidic. Strong base weak acid is basic. That explains why baking soda, NaHCO3, acts as an antacid. It's a basic salt.
Exactly. Sodium hydrogen carbonate comes from a strong base, NaOH conceptually, and a weak acid, H2CO3. So it's a basic salt capable of neutralizing excess stomach acid. Understanding the pH of salts connects directly to their uses.
Right, so common salt, NaCl, is neutral. Is it just used for food and maybe preserving things, or does it have bigger industrial roles? It seems too common to be just for the kitchen.
You've hit on a massive point. Common salt, sodium chloride, is far, far more than just a seasoning. Industrially, it's a cornerstone chemical. It's the fundamental raw material for manufacturing a huge range of other essential chemicals. Think of it as a starting block for industrial chemistry. We get NaCl primarily from seawater through evaporation or by mining vast underground deposits of rock salt. These deposits are often brownish due to impurities and are relics of ancient dried-up seas. Its importance is even woven into history. Think of Mahatma Gandhi's Dandi March highlighting its significance. But industrially, is the feedstock for giants. Let's look at some key chemicals derived directly from NaCl. These processes and uses are very important for exams. First up, sodium hydroxide, NaOH, also known as caustic soda. It's made by the chloralkali process.
Chloralkali.
Yeah.
Sounds like chlorine and alkali.
Exactly. The name tells you the main products. In this process, we pass electricity through a concentrated aqueous solution of NaCl. This solution is called brine. The electricity causes the NaCl in water to decompose. The overall reaction is 2 NaClAq plus 2 H2O electricity, 2 NaOHu plus Cl2G plus H2G.
Okay, so we get sodium hydroxide, chlorine gas, and hydrogen gas. Where do they form?
Good question. It happens in an electrolytic cell. Chlorine gas, Cl2, is produced at the anode, the positive electrode. Hydrogen gas, H2, is produced at the cathode, the negative electrode. Sodium hydroxide solution, NaOH, forms in the solution near the cathode.
And what are these products used for? That seems important.
Extremely important. The uses are wide-ranging and frequently tested. H2, hydrogen. Used as fuel, like in fuel cells, for making ammonia, key for fertilizers, and in hydrogenating oils to make margarine of anaspati ghee. Cl2, chlorine. Water treatment, disinfection, making PVC plastics, disinfectants, pesticides, and formerly CFCs. NaOH, sodium hydroxide. Degreasing metals, making soaps and detergents, paper manufacturing, making artificial fibers like rayon, and you can even combine these products. H2 plus Cl2, HCl, hydrochloric acid, used for cleaning steel, making medicines, cosmetics. NaOH plus Cl2, e-bleach, sodium hypochlorite solution, used for household bleaching, bleaching fabrics. This chloralkali process diagram, the reactions, the products, and all their uses, you really need to know this inside out.
Okay, chloralkali is huge. What else comes from common salt?
Next is bleaching powder. We just saw chlorine is made in the chloralkali process. That chlorine is then reacted with dry slaked lime, which is calcium hydroxide, KOH2. The reaction produces bleaching powder. Its chemical formula is often written as KClO2, calcium hypochlorite, though the actual composition is a bit more complex. The reaction is KCOH2 plus ClO2 plus KClO2 plus 2H2O simplified.
And its uses. Bleaching, obviously.
Yes,
Okay.
primarily. Bleaching cotton and linen in the textile industry, bleaching wood pulp for making paper, bleaching washcloths and laundry. But also, it's a strong oxidizing agent used in many chemical industries, and critically for disinfecting drinking water to kill germs. Very important public health application.
Got it. Bleaching and disinfecting. What about baking soda? Is that also from salt?
Yes. Baking soda, sodium hydrogencarbonate, NaHCO3,
Mm-hmm.
also uses NaCl as a raw material. It's typically made using the solvay process, though you might not need all the details, involving NaCl, water, CO2, and ammonia. The key reaction step producing it is NaCl plus H2O plus CO2 plus NH3 and H4Cl plus NiGCO3. We already established it's a mild, non-corrosive basic salt. An important property is what happens when you heat it, like during cooking or baking. 2 NaHCO3 is plus H2L plus CO2G. It decomposes to form sodium carbonate water and that crucial carbon dioxide gas.
Ah, the CO2. That must be why it's used in baking.
Exactly. Its uses are directly linked to its properties. Making baking powder. Baking powder is not just baking soda. It's a mixture of baking soda and a mild, solid, edible acid like tartaric acid or cream of tartar. When it gets wet or heated, the acid reacts with the NaHCO3 to produce CO2 gas. NaHCO3 plus H plus H2 plus H2O plus sodium salt of acid. The CO2 gas gets trapped in the dough or batter, making cakes, bread, pakoras light, soft, and spongy. Ingredient in antacids. As we discussed, being alkaline, it neutralizes excess stomach acid, soda acid fire extinguishers. Inside these, baking soda reacts with an acid like sulfuric acid when the extinguisher is activated. This produces a large volume of CO2, which smothers the fire by cutting off the oxygen supply. These uses come up very frequently in exams.
Baking, antacids, fire extinguishers, very versatile. Okay, one more. Washing soda.
Right, washing soda. Its chemical name is sodium carbonate decahydrate, A2CO3.10H2OL. How do we get it? First, you get sodium carbonate and 2CO3, often called soda ash, by heating baking soda, as we just saw in the decomposition reaction. Then you take this anhydrous sodium carbonate and recrystallize it from water. It absorbs water molecules into its crystal structure. The reaction is Na2CO3 plus 10H2O and A2CO3.1H2O. This crystalline form with 10 water molecules is washing soda. Like sodium carbonate itself, it's also a basic salt.
And its uses. Cleaning, I assume.
Yes, cleaning is a major one, but also others, used in the glass, soap, and paper industries, used to manufacture other sodium compounds like borax as a cleaning agent for domestic purposes, and a very important industrial and domestic use, removing permanent hardness of water. It precipitates out the calcium and magnesium ions that cause hardness.
Removing hardness of water? That's a big one.
Well.
Okay, this is a lot of detail, tutors, especially all the reactions and uses derived just from common salt. Now, that point head and H2O in washing soda's formula, does that mean the crystals are actually wet? What exactly is this water of crystallization? It sounds like more than just dampness.
That's a very sharp observation, and it leads us to a fascinating property of many crystalline salts. No, it doesn't mean the crystals are wet in the way we usually think of wetness, like having surface moisture. It refers to something specific called water of crystallization. These are water molecules that are chemically bound within the crystal lattice structure of the salt. They are present in a fixed ratio and are essential for the salt's characteristic crystal shape and often its color. They're an integral part of the crystal itself.
So they're part of the structure, not just sitting on the surface.
Exactly. Let's illustrate with activity 2.15 using copper sulfate crystals. Hydrated copper sulfate has the formula CuSO4.5H2O, and its crystals are a beautiful bright blue. If you take a few of these blue crystals in a dry test tube and heat them gently, what do you observe?
The color might change. Maybe water comes off.
Oh, both are correct. As you heat it, the blue color fades and eventually disappears, leaving behind a white powder, and you'll see tiny droplets of water condensing on the cooler upper parts of the test tube. What's happened? The heat has driven off the water of crystallization. The blue hydrated copper sulfate, CuSO4.5H2O, has turned into white anhydrous copper sulfate, CuSO4, which means without water.
Okay, so heating removes the water and the color. Can you get the blue back?
Yes, and this shows how integral the water is. If you take that white anhydrous powder and add just a few drops of water back to it,
Blue color comes back.
instantly. The blue color is restored as the anhydrous salt rehydrates, absorbing the water back into its structure to become CuSO4.5H2O again. The water is essential for that blue color in crystal form, so the formal definition. Water of crystallization is the fixed number of water molecules present in one formula unit of a salt as part of its crystal structure. Examples. Copper sulfate is CuSO4.5H2O, 5 water molecules. Washing soda is Ni2CO3.10H2O, 10 water molecules. Another important one is gypsum, which is KSO4.2H2O, 2 water molecules. These water molecules are chemically bonded, not just surface wetness.
Okay, water of crystallization, fixed number of water molecules chemically bound in the crystal. Got it. And you mentioned gypsum, KSO4.2H2O. I've definitely heard of that. Is that related to plaster of Paris, the stuff used for casts?
Precisely. Gypsum is the direct raw material for making plaster of Paris, POP, a hugely important material in medicine and construction. Its chemical name is calcium sulfate hemihydrate. Hemi means half. Its formula is KSO4.12H2O.
Half a water molecule. How does that work?
It looks odd, but it represents a ratio. It actually means that 2 formula units of KSO4 share 1 molecule of water in the crystal structure. So the ratio of KSO4 to H2O is 1 to half, or 2 to 1. POP is made by heating gypsum, KSO4.2H2O, very carefully to a specific temperature. 373 Kelvin, which is exactly 100 degrees Celsius. It's important not to overheat it. At this temperature, gypsum loses part of its water of crystallization specifically. It loses 1.5 water molecules per formula unit. The reaction is KSO4.2H2O, heat at 373 K, KSO4.12H2O plus 112H2O. The water escapes as steam. Plaster of Paris itself is a fine white powder.
Okay, heating gypsum carefully gives POP. What makes POP so special? Its setting property.
Exactly, that's its key feature. When you mix plaster of Paris powder with water, a remarkable reverse reaction happens. It rapidly reabsorbs water and sets back into hard, solid gypsum within about 5 to 15 minutes. The setting reaction is KSO4.12H2O plus 112H2O, KSO4.2H2O. This process is exothermic. It releases a little heat as it hardens.
And that setting is why it's used for?
Many things. Its uses are frequently asked. Medical casts. Doctors use it to make casts to support fractured bones, holding them immobile in the correct position while they heal. It can be molded easily when wet and then sets hard, making statues, toys, decorative items. It can be cast into molds to create intricate shapes, making surfaces smooth. Used in construction for smooth finishes on walls and ceilings, POP ceilings, and for creating ornamental designs, making surfaces smooth. Also used in making chalks and fireproofing materials.
Okay, very useful. Is there anything important about storing it?
Absolutely crucial, and a common exam question. Plaster of Paris must be stored in a moisture-proof container.
Why? Because it reacts with water.
Precisely. If it comes into contact with moisture from the air, it will slowly absorb that water and prematurely begin setting back into gypsum. It will become hard and lose its powder form and its setting property. Once that happens, it's useless for making casts or molds. So keeping it absolutely dry is essential to maintain its utility.
Wow, that was an incredibly thorough deep dive tutor. Seriously, from the basics of taste and indicators, right through all the reactions, pH, the industrial chemistry of salt, and ending with POP. I feel much more confident about tackling this chapter now. The step-by-step approach and the real-world links really help solidify everything.
Excellent. I'm really glad to hear that. It was indeed a comprehensive journey through acids, bases, and salts. Let's just quickly recap the absolute vital takeaways for your exams, just to lock them in. Remember, fundamentally, acids produce H plus AQ ions in water, more accurately H3O plus, while bases produce OH-AQ ions. We identify them using indicators natural, litmus, turmeric, synthetic, phenolphthalein, methyl orange, or even olfactory, onion, vanilla. Key reactions. Acids react with active metals giving H2 gas, with hydrogen carbonates giving CO2 gas, tested with lime water turning milky. Neutralization is acid plus base, salt plus water. And remember, metallic oxides are generally basic, while nonmetallic oxides are acidic. Safety first when diluting. Always add acid slowly to water A to W because the process is highly exothermic. The pH scale, 0-14, quantifies strength based on H plus concentration. Lower pH means stronger acid, higher pH means stronger base, 7 is neutral. And pH impacts everything. Life processes, acid rain, soil health, digestion, tooth decay, even insect stings. Salts aren't always neutral. The pH depends on their parent acid and base strength. Strong neutral. Your strong weak depends which is strong. Common salt, NaCl, is a vital raw material for NaOH chloralkali. Bleaching powder, baking soda, and washing soda know their production and uses. Don't forget water of crystallization, those fixed water molecules in crystals like CuSO4.5H2O and Na2CO3.182O, gypsum, KSO4.2H2O. Heating removes them, often changing color. And finally, plaster of Paris, KSO4.12H2O, made from gypsum by careful heating, sets hard when mixed with water, making it vital for casts and molds. Store it dry.
That's a fantastic summary. It really pulls all the threads together.
Great. Now remember, understanding the theory is one thing. Mastering for exams requires practice. Make sure you revise these concepts again, especially focus on writing and balancing all the chemical equations we discussed. That's a fundamental skill they always test. Most importantly, solve as many past year questions, PYQs, as you can find related to acids, bases, and salts. Look at questions from your board exams and also from competitive exams like SSC, UPSC prelims, if applicable. This helps you see the patterns, the common traps, and improves your speed and accuracy under pressure. And if, while practicing, you hit any roadblocks, any doubts on a concept or a specific question, don't hesitate to seek clarification. Keep learning, keep practicing. All the very best for your exams.